Hi, welcome. Today we're going to talk about lithium iron phosphate batteries, just like this one. Here's another example of a DIY battery that I've built, and if you recognize this box, it's because you've seen it at Harbor Freight. This is a DIY battery build that I've done myself using the Apache box. Inside you'll see that we've got headway cells. They're these cylinder cells, and there's 8 of them in there. There's 2 in parallel, then 4 in series with a BMS. And we'll get into the details about what all this means to you in just a moment. But you can see that it all fits in here nicely. The advantage is now I can put custom ports on the side that allow me to charge with solar, or you can use USB power delivery. There's even Anderson power poles on this box for applications such as ham radio or other electrical equipment that has a higher draw of amperage than a 1C on most of these smaller batteries. I would highly suggest that you look into custom DIY lithium iron phosphate batteries. Just need to know a little bit about electronics. Let me explain. All right, let's start with Ohm's law. So the E in this situation is volts. What is volts? Volts is the ability. This is going to be, as you may have seen, 12 volts or 24 volts, or in your house you have 120 volts. Now let's look at I. I is your current. I equals current, which is referred to as amps. And amps is your flow of electricity. And this is where your power comes from. Let's talk about buckets of water. So if you have a bucket of water here, and this bucket is filled to the line here, and you're going to pour that water, or let's actually make a tube that connects this to another bucket of water, and this one is only filled to here. So what's going to happen is that the water here is going to go down and try to equalize to this one to make it go up. So the current through the pipe where we're going to be measuring is moving in this direction towards the bucket that has less water. If you think about those as batteries, we'll talk about a 3.6 volt and a 3.2 volt battery. So that will show you where current flows. So if you've ever tried to connect 2 batteries together, like in a dead car, and you hook up your jumper cables and you see a spark, that spark happens when the battery from the car that has no power is trying to absorb a lot of current from the battery that is full. So this one is empty, this one's full. The current is going to try to go to this battery very quickly, and whenever there is the metal gets close to the terminal, it creates a spark because it's trying to move really quickly. That spark is just indicating that there's current moving. If the 2 batteries were the same voltage, both of them having the same amount of voltage in them, so we'll call it a 13 volts, and you hook them up, there would be no spark because there's no current flowing. There's nothing for them to exchange. They're at the same level. I hope that helps explain current a little bit. Let's look at R. R equals resistance. Resistance could be due to wire length. It could be due to actual resistors or any other item along the path of the electricity that creates resistance. Now, let's talk about series and parallel circuits. So in a series circuit, for DIY lithium iron phosphate batteries, we're going to have a few batteries here. And these batteries obviously have a plus and a minus. That's the polarity of the battery. As you can see, we're going to put the negative, positive to negative, positive to negative, positive to negative. So this creates a series. Now if each of these batteries in a lithium iron phosphate system, the battery's nominal voltage of 3.2 volts, if you add all of the voltages together, you get 12.8 volts. So when you have all of these together in one pack, you create a 12 volt battery. This is the nominal voltage of each lithium iron phosphate cell. When it's fully charged, you're going to see a voltage of 14.6. Don't worry about the 14.6 voltage being too high for most of your electronics. They usually have a range of about 10 point something to 15 volts. So your batteries will supply voltage that's somewhere in this range for those electronic devices. Just make sure that whatever you're plugging this into can support those voltages. Now let's talk about parallel circuits. Alright, in a parallel circuit, you're going to have your battery with a plus side and a minus side. And you're going to have another battery here with a plus side and a minus side. So let's do 4 of them for consistency. You're going to hook your minus to your minus, your minus to your minus, and your minus to your minus. And same over here. So what this does is it creates, remember this is a 3.2 volt cell, but when we do a parallel circuit, it doesn't change the actual voltage of the total pack. What we're doing is we're creating an 8 amp hour cell times 4. So when you have 8 amp hours per cell, you're going to get 32 amp hours. So one of these cells that I use, the Headway lithium iron phosphate batteries, they're 8 amp hours and 3.2 volts nominal voltage. When you put multiple of these together, as we demonstrated on the whiteboard, you're going to create a 12 volt battery. But what if you want more capacity? What if you want more than 8 amp hours? That's where this parallel circuit comes into play, and you can create more amp hours. So if you want to create 2 of these together and 2 of these together, that would be 16 amp hours and 16 amp hours. You would need 4 sets of 2 to create a 16 amp hour battery at 12 volts. So 16 amp hour at 12 volts would be two of these cells by 4 of these cells. The way we write this cell type out is a 4S2P configuration. That would be a 12 volt and a 2 times whatever the amp hour of that cell is. So in this case, it's 8 amp hour. So we have a 16 amp hour, 12 volt battery. You can continue to create more parallel versions of these cells and make this battery as large as you would like. Just keep in mind that you're going to need a lot of bus bars if you start adding a lot of these cells. Let's take a look at that 16 amp hour battery I showed in the very beginning of the video. It's got a nice little case here. You don't have to worry about shrink wrap because it's all nicely fit into this box. Let's see if I can get it out and show you what we've got going on here. Alright, so as you can see, there's 4 on the bottom, 4 cells on the top, and we've got parallel. So this is a negative, this is a negative, that's a parallel set. And then we connect them in series, they're parallel with this bus bar, and then series to the next. This is a parallel connection here, but that connection is the series. On this side, those 2 cells are then in parallel, and then they're series to the next cells, which are paralleled with this bus bar. And then they are paralleled here, and then in series again to the last cell, which is paralleled here and paralleled here. So these two connections are basically the same. You've got your battery positive coming right off of the cell here, and this goes to the BMS, and this is your battery negative. This connection here that we haven't talked about yet is the Bluetooth interface for the BMS. It just plugs right into the side here. I often put fuses on both the positive and negatives just so that you don't have any mishaps with your equipment. It's a good safety measure. And then you can connect from that point to any of your additional add-ons. In this case, I've got the USB connections, I've got Anderson connections, and I've got a barrel connector here in the bottom so I can hook up solar. And take a look at those again. There's your barrel connector, there's your USB. This is a 65 watt power delivery or a quick charge. And then I've also got Andersons. This pack with the parallel series is a 16 amp hour, about 220 peak discharge, and about 80 total nominal discharge because of the parallel connections. I will say that the BMS in this case is only a 60 amp. This is a different BMS than we were talking about earlier. This one is a 40 amp and this one's 60. Your BMS will determine the total discharge capability of the batteries. As long as the BMS is equal to or less than the capability of your batteries, you're safe. And that's for the discharge and charge capabilities. You can go into the BMS even if it's higher and reduce the discharge and charge capabilities through the software. And I'll show you that in a minute. The BMS will control the current out of the battery and into the battery when you're charging. This is to protect the cells from under voltage or over voltage at any time. You'll have to connect over here. There's a lead that goes on there that will have 5 wires coming out, one for each end of each cell, so that you'll know the voltage of each cell at any time. And how will you know that? Because this particular one has a Bluetooth module that attaches and you can connect with your phone to monitor the cell voltage and the current from your battery pack. Let's take a look at a few different BMSs just so you understand what they look like. This BMS is one I would not recommend, but it does do the entire pack's voltage. When it gets too low, it'll cut it off, but it does not do individual cell voltage, which is strange because it does know the individual cell voltage, but it's just not programmed to protect each cell. This one is made by a company that I cannot pronounce the name, but it is a BMS for 100 amp discharge, and it has temperature sensor on it so that your batteries don't get too cold while they're charging. You wouldn't want that, it can damage the batteries. And this particular one does not have a Bluetooth interface, but it does monitor the voltage of each individual cell. It's important to note that on your BMS, it's going to indicate the type of pack that you're building. In this case, this one shows a 4S. That's the 4S we discussed a moment ago that references how many cells you have in series. And it indicates a 12 volt battery and the amount of amps that this BMS supports for discharge. The charge current for this amp is 20 amps coming in. You're going to need some kind of power supply like this one from Reach Power that allows you to control the amps and the voltage so that you don't overcharge or put too much current to this particular cell. In this case, it's set too high. It's not plugged in yet. Let's set this to the appropriate voltage. We're going to go down to the top charge voltage, which is going to be 3.65 volts. There's a fine-tuned knob here, so we can bring it up to 3.65. I would recommend that you don't always trust this number. Take a multimeter and check the power at the leads, because you may have some voltage drop across the leads. You may have an incorrect readout here. In this case, I'm fairly certain that that's correct. I've already checked it. We're going to go ahead and plug it in, and we're going to charge this cell up. This is called top charging. We're charging an individual cell without a BMS to its full potential of 3.65 volts, so that when you assemble the battery pack, they're already equal in voltage and their top capacity. Once your batteries are to their top charge voltage, go ahead and assemble them however they're going to be in the pack in the end. In this case, we're going to have a 4 square pack, and we're going to put the BMS something like that. This mock-up setup is so that you know when you install your leads here for the battery, how long you need these cables to be. In this case, I've already attached the leads, these ring terminals to the end, but I would suggest that when you build your pack, you measure out how far these leads need to go before you start adding your ring terminals so that you don't have a ton of extra wire. Okay, on the BMS, there's a B minus and a P minus. The B minus is going to be for your battery, and the minus, I know I'm missing one of the cell holders here. Ignore that, pretend it's there. All right, so this would be theoretically going to the minus of the batteries pack, which would be here. So we could trim the wire to here, put a ring terminal and attach it here along with the bus bars. Bus bars would not be on this particular battery. We would have a bus bar that attaches from this battery's positive to the next battery's negative. So we'll go ahead and do that now so I can show you what that looks like. And then you'll take the bus bar, which is a piece of metal that's generally copper, it may have some tinning on it, and it will attach like this. And to the negative of the next battery. So this is creating that series circuit we talked about earlier, and simply screw that on there. Take this BMS away for a minute. So this will be the first step in your series circuit on the first battery. So this is battery number 1, where the negative, positive to negative, positive to negative. So then on this side we will attach another bus bar, like so. And as you're doing this, remember that the bus bar needs to be the first thing that you put on the battery stem. When you have these leads, you need to make sure they don't go on there first, because you want all that current to be able to go through the bus bar. This is just to read out the voltage, it's not to actually transfer power. So this can be just on the top like so. You wouldn't want it like this, because then the power has to go through that lead and into the bus bar. Sometimes the bus bar then wouldn't be flush or level. It's just best practice to create your best connection there with your bus bar right to the battery, and then add your lead on top. All right, so I'm going to go ahead and do the rest of these bus bars, and then we'll get back here and I'll show you what it looks like when we have it all together. Okay, so now we have the battery set up like it will be in the end when it's all packaged up. We have the battery's total negative here and the positive here. If we read across those two terminals, we should show somewhere in the range of 13 to 14 volts. Let's take a look real quick. That's positive, that's negative. We've got 14.29 volts. Proving that the series connections are making their way across the cells properly. Again, this is the pack positive, pack negative, and starting at the negative cell here, we go across to the positive, which is connected to a negative, going across that battery, which is number 2, from its positive to the next negative, which is cell 3, which goes to its positive to the next negative, which is cell 4, and that is the pack's positive. They're all in series, creating that 14 volts. These are going to be where you hook up the BMS's negative. We'll start actually here, or we can put it here, but the negative is going to go here to this cell. This is the whole negative that comes out of the pack that you're going to hook to your load, which could be your radio or anything else. This temperature sensor will get folded into the pack cell here, so it can just read the temperature, ambient temperature around the cells to ensure that they're within range. And then your leads will attach here, and then you put them onto each corresponding cell. All right, so here on this lead set that doesn't have the terminals on it yet, you can see the black wire is the first one on the right if you're looking at the BMS this direction. That goes to the first negative along with this blue wire here. So if this blue wire goes to the negative of the pack, the black wire must also go to the negative of that pack. So you're going to put ring terminals on these two connections and attach them here. The next wire on that set goes to the positive of the first cell. Remember that the first cell is considered the cell where your negative from the BMS attaches. So this is cell 1. This first red lead will go to the positive of that cell. So you'll put a ring terminal and put it under that screw right there. The next one goes to the positive of cell 2, which is going to be over here on this side. So you'll have to do some cable management and get your ring terminal on that one. Then the next one goes to the positive of cell 3, which is here. And again, it's a short run, so you'd want to cut your wire short so you don't have to manage all that cable. The last one goes to the positive of the last cell. So then you can run that over here to the positive. Once you have all your leads put in place, the battery management system fully connected, you can attach a wire with a terminal here, which will be your positive wire. This will be your negative wire, and then you have the two wires coming out to attach your load to. Once you've got your entire cell put together, your battery pack put together, you can put some heat shrink on it. It needs to be heat shrink that covers the whole cell. In this case, we just took some plastic and cut it to size, put it on the end there, and held it in place with some hot glue while we put the heat shrink on. The nice part about building your own battery is that you can actually put whatever kind of terminals you want on there. In this case, we have a barrel connector that you can use for solars, commonly used on Bioenno solar panels, but any type of connection here that you want to use, whether that's MP4 connections, anything you want, you can put right here. We chose to use Anderson connections because that's pretty standard in the amateur radio world, and a lot of other different electronics use those connections as well because they're hard to put in the wrong way. But yeah, you can put whatever connections you want on there. It's hard to see with the shrink wrap or the case on there, but that blue wire we were talking about comes over and goes into that first negative of the first cell here, and then you have the negative from the leads here, both negatives connect to the black wire that comes right out of the BMS. All the other leads that are coming off of the sensors go to their respective positives for each of the cells throughout the pack. Here on my desk, I have a 30 amp power supply with a variable voltage. Don't know if you can see the voltage here. Let me see if we can get a little closer. It's a 14.6 volts at the moment, which just happens to be the voltage that lithium iron phosphate batteries like to be charged at. This particular pack is pretty full, but we're going to plug it in and see what kind of amp draw we get whenever we plug it in. All right, we've got 14.6 volts and 0 amps. We're going to plug it in and see what we get. All right, we're pulling 8, 7 amps, 6 amps. You'll notice that the amps go down as the battery becomes more full. As we talked about with current flow, as the voltage equals out, the flow reduces, just like in a stream or in a waterfall. As it gets closer to the top, it'll take longer for this to go to 0, but when it hits 0 or when it cuts off because of the BMS, you've reached the maximum capacity of the battery. Here on my desk, I've got a power supply hooked up to a distribution block for these Andersons, because I have a lot of equipment that uses them at the same voltage. And we have the wire going from the power supply to the distribution block, and then we have a 2-meter 440 radio, and then we have the HF Yaesu radio. What I can do with this battery is plug it into the distribution block and simulate a power outage to show that the battery can run all of this equipment. So we'll plug it in here. If I can do it, let's see. Okay, so this battery is plugged in, the power supply is charging the battery, and all the equipment's turned on. So what I'm going to do is turn off the switch to the power supply to simulate a power outage. And we can see that the rest of the equipment will stay on because it's now being supplied by the battery through the distribution block. Let's do that now. Okay, the power supply is off, it's producing 0 amps, but the battery is supplying power to the distribution block across the units. You can also see that our voltage went to 13.6 as opposed to 14.6, now it's 13.7. This voltage is the voltage of the battery as it's producing power for those units. The amps is 0 because this unit, the power supply is producing nothing, but the battery is producing current. I don't have a meter on the battery right now to show that. Okay, I brought my phone over here so we can see what's exactly going on with this battery as it supplies power to the radios on the desk. Alright, so it's producing 2.6 amps. Its capacity currently is 7.8 amp hours out of 8. So we've got about 98% of this battery left. What you're seeing here is the on-screen representation of what this battery can do, connected through this Bluetooth adapter. Alright, just a quick recap of what we need to build out a lithium iron phosphate battery. We've got the cells, which in this case we're using 4 cells. We picked up some cell holders. We've got some plastic to protect the end of the battery here. And then we've got some extra wire, Anderson power poles, and I believe it's a 5mm barrel connector. And then this particular BMS is the VNS ZNR off of Amazon. I'll post some links below anyway to these different devices. It depends on when you go look at it. Sometimes the Daly BMSs are available, sometimes you get this brand. They look exactly the same and they use the same software. I imagine they come from the same factory. So that's pretty much it. It's not very complicated as long as you have a few basic understandings of how electricity flows. I think you can build this, and there's so many purposes for the 12 volt, 24 volt batteries that you could use them in your life, I'm sure. Thanks for watching.